Good morning. This time I will be talking to you about carbocations, a very, very important type of molecule with a positive charge, so technically it's not a molecule, it's an ion, and obviously ions can only exist in ion pairs, so whatever positive carbon is in the carbocation has to have some sort of a negative counterion somewhere in the sample. Anyway, carbocations do a very interesting thing called rearrange, and we'll be talking about rearrangements as well. Before we start, I would suggest that you read page 210, the middle two paragraphs, and then go ahead and read pages 212 and 213 as well. Carbocations, as I said, are highly unstable. They are positively charged, and they have a positive charge because the carbon has 3 valence electrons instead of 4. You'll also notice it doesn't have an octet, which makes it very unstable. And as such, carbocations are only found in mechanisms. In other words, they get formed in some sort of a mechanism step and then get used up again right away. So you never actually isolate any compounds with a positive carbon. So notice a couple things. First of all, as I said, they have a positive charge. 3 valence electrons, not 4, thus positive. Notice that because they are ions, or positive, they have to have some sort of a negative counter ion somewhere in the mixture, and that can be any number of different things: chloride, bromide, sulfate, all sorts of different things. Also notice, as I said, carbocations have less than an octet. That's because they have 6 total electrons around instead of 8. And finally, as I said, they're highly unstable, only exist as intermediates in mechanisms. You can't go to the stockroom and find a jar or a bottle that contains positive carbon molecules. Just to review the idea of mechanisms, you might want to go back and review videos 4.06, 4.07, and 4.08. Now, there are different kinds of carbocations, and some of them are more stable than others. That's not to say that any of them are stable enough to put in a bottle, but they still only occur in mechanism. But some are better than others. And these are the 4 kinds that we'll be dealing with here, and they really only differ from the number of hydrogens and the number of carbon groups attached to the positive carbon. So notice that this carbon has all 3 of its other things are hydrogen, so we call that a methyl carbocation, sometimes indicated in shorthand by 0 degree, and this is the least stable kind of carbocation. Then you have the kind where you have 2 hydrogens and 1 kind of carbon group. So the R group here could be methyl, ethyl, propyl, or lots of other carbon groups that we're familiar with. This is a shorthand notation for it, RCH2 with a positive charge. This kind where you have 1 carbon group on it is called primary. It makes perfect sense. We've learned what primary, secondary, and tertiary means before. If the carbon has 1 other carbon group attached to it, it's primary. So you have primary carbocations. Those are a little bit more stable than methyl carbocations. Obviously, then if you have 2 carbon groups and 1 hydrogen, that's called a secondary carbocation. And if you have all 3 of the other groups on the carbon being other carbon groups, and by the way, these R's do not all have to be the same as each other, so this could have 3 different R groups, or 2 and 1, or all 3 being the same. Shorthand notation written this way or this way, that's a tertiary carbocation, and that's the most stable. So basically, when you think about carbocations, you should just remember the order of stability: tertiary better than secondary, better than primary, better than methyl, and we will hear that same order of stability lots of times. So, how are carbocations formed? Well, a number of different ways, as I mentioned. In this chapter, the main way that we're going to be forming carbocations is by protonating an alkene. So you can see if you have a carbon-carbon double bond with 4 other groups attached, those could be hydrogens or whatever, and you put in a strong acid like HCl or sulfuric acid, this double bond actually acts as a base, and it gets the extra hydrogen attached, and so one of these 3 would then be hydrogen. So the hydrogen is going to protonate that carbon right there, and that leaves the other carbon positive because one of these pairs of electrons has to be involved in forming the new bond between the carbon and the hydrogen. That leaves this carbon then without one of its electrons and ends up being positive, and then the counterion for that positive charge would be the conjugate base of this acid. So really, in every sense of the word, this is an acid-base reaction. We're used to bases as having lone pairs of electrons, but it turns out bases can also have a pi bond. So the pi bond acts like a pair of electrons, picks up the H+, and then that leaves the conjugate base. Okay, a second way carbocations can be formed is from alcohols by loss of water. We won't be looking at that particular reaction type in this chapter, but in the future we will, so you might as well be familiar with it. So this is an alcohol with an OH group. There are pairs of electrons on that oxygen. If a strong acid is in the presence of an alcohol, it can protonate one of the lone pairs on that oxygen, so it becomes OH2, an extra hydrogen on it now, positive charge because one of the pairs of electrons has been used to form the new bond to hydrogen. That again leaves the conjugate base of the strong acid as A-. That's still not a carbocation though, because then in the second step, the protonated alcohol loses this water molecule, takes this pair of electrons with it to satisfy its positive charge, it becomes water, and then that leaves the carbon that it was attached to positive because you've ripped away one of those electrons and it then becomes positive. The counterion A- is still there, so whatever the conjugate base was of the original acid, that's the counterion for the carbocation, but we now have water in the mixture. So there's a second way of forming carbocations is by protonating alcohols and then losing water. Here's the third way, kind of similar to the previous one, but actually simpler. Some alkyl halides, like a bromine or a chlorine here, I've drawn bromine, but it could just as easily be chlorine or iodine, can just leave without anything else causing it, just this pair of electrons leaves with the bromine, it becomes negative, and then that leaves the carbon positive. And then obviously the counterion for that positive charge is the negative halide. Again, number 2 and number 3 today are in this chapter, they're for future reference. Okay, so now let's talk about rearrangements of carbocations. Once a carbocation gets formed, it can undergo a rearrangement. So if you haven't already read it, read section 6.3c on pages 216 through 218, and it'll talk about carbocation rearrangements. So what is a rearrangement? Well, it turns out that if you have a positive charge on a carbon, and you happen to have a hydrogen next door to it, that hydrogen can literally step over. So this pair of electrons just scoots over to this carbon, bringing its hydrogen with it. So now there's that pair of electrons. But of course, when it does that, it leaves this carbon positive. And so essentially one carbocation turns into a new carbocation. So that always happens when you do a stepping over of a hydrogen to a carbon next door. One carbocation turns into a new carbocation. You might wonder, well, why would that happen? And the answer is, obviously, if this is a better carbocation, then this one, say this one is tertiary and this one is secondary, then that would happen. Or, even more interesting, if you have a carbocation with a carbon group next door, that carbon group can actually step over. So literally a carbon-carbon bond is breaking and a new carbon-carbon bond is forming over here. What was the positive carbon now is neutral. What was the neutral carbon is now positive. So again, you're taking one carbocation and forming a new carbocation. And that, again, will only happen if you can form a better carbocation. So if this is tertiary and this is primary, let's say, then that would occur. Otherwise, not. So these are technically called hydride shifts or alkyl shifts. So a hydride shift means you move a hydrogen over next door. An alkyl shift means you move a carbon next door. Now you may be panicking a little bit here and going, well, how do I know when this can happen and how it can happen? Can different things happen in the same molecule? All of which will become clear when we start doing some actual examples. So here's an example. This would be the 2,2-dimethyl 3-pentyl carbocation. Let's just talk about that name here briefly. Notice that it's a 5-carbon chain with a positive charge on the third carbon, so it's 3-pentyl carbocation, and then it has 2 methyl groups on the second carbon, so it's 2,2-dimethyl 3-pentyl carbocation, and notice that that's secondary. That can rearrange by moving one of these 3 methyl groups, and it really doesn't matter which one because they're all the 3 the same as each other. If we just step this methyl group over, bring the pair of electrons over and satisfy the positive charge on that carbon, then that leaves this carbon without an electron, and therefore positive. That would then be called the 2,3-dimethyl 2-pentyl carbocation. Again, 5-carbon chain, positive charge on the second carbon, meaning 2-pentyl, and then methyl groups on carbons 2 and 3, so 2,3-dimethyl 2-pentyl carbocation. Now notice that that's a tertiary carbocation, and so this is a rearrangement that would actually happen. Remember, this is a step in a mechanism. It's not a reaction in itself, so you can't go to the stockroom and get a bottle that contains 2,2-dimethyl 3-pentyl carbocations or any other carbocation molecule for that matter. mentioned before, the carbocation gets formed in a mechanism step, then it may rearrange, and then it gets used up again in further mechanism steps. So literally the rearrangement is a step in a mechanism. Also, remember that there has to be some sort of a negative hanging around here somewhere to balance out that positive charge. Same thing here. That's not shown in this particular reaction because it could be any number of different things. So technically this kind of step that I've shown here, this kind of balanced equation, is what we call them net ionic equations, where we haven't shown whatever the spectator ion is. Another example. So this is a secondary carbocation. It would be called the 1-cyclopentyl ethyl carbocation because as long as chain is 2, it's an ethyl group with a positive charge on carbon number 1 and a cyclopenyl group on carbon number 1. So it's 1-cyclopentyl ethyl carbocation. But notice though, and it's not shown here, but you have to be aware that there is a hydrogen on this carbon right here. There's a CH. That's because this is a stick figure. Remember, in these stick figures, we don't necessarily show the hydrogens, but there is one there. That hydrogen can step over, neutralize that positive charge, and so then that becomes CH2. But in so doing, this carbon right here ends up having one of its electrons taken away from it when hydrogen moved with its electrons, and so that carbon ends up being positive. Now notice that this is a secondary carbocation. This is a tertiary carbocation because it has 3 other carbons attached to it. So tertiary from secondary, again, that's a rearrangement that could occur. Not every carbocation will rearrange, as I've implied. It only happens if you can go to a better carbocation. So this one, perfectly fine carbocation, it won't rearrange. Why not? Because it's already tertiary. Notice that that carbon has 3 other groups attached, therefore it won't rearrange. What about this one? This is only secondary, so it would rearrange if it could become tertiary. But it turns out there's no way to make it be tertiary by just moving a hydrogen next door. You could move that hydrogen over, and then this carbon would be primary. That's not any good. You could move one of these hydrogens over, but then that carbon would still be a secondary carbocation, and that's not going to happen. At least typically it doesn't happen, although there are cases where secondaries rearrange to secondaries. For our purposes, we're just going to say it doesn't happen. And then you could think about, well, maybe we could move this whole ethyl group over next door, but then that would be this carbon actually primary, and so that's not going to happen. So think about it, and you'll see that any rearrangements that could happen here won't result in a better carbocation. So what I want you to do at this point is predict the rearrangement, if any, and it may be that there is no rearrangement that could occur, but predict the rearrangement, if any, that would occur in each of these 3 different carbocations. Okay, so stop the video, write down the carbocations, and then write down what the rearranged carbocation would be, if any. Okay, we're going to go to the next screen here. So this one is a primary carbocation. That carbon has a positive charge, and that only has 1 other carbon, so that's primary. If we simply scoot one of these hydrogens, so one of these 2 and the CH2 group over here, that will become CH3, so it becomes CH3. That will leave this carbon with only 1 hydrogen now instead of 2, so it's just CH. And of course this carbon would become positive because it will have lost electrons when the hydrogen moves over. And so the carbon now next door is the one that's positive. This was primary. What kind of carbocation is this? Secondary. And so that would happen. Okay, so that's a good rearrangement. Let's go to the next slide. So here we have a secondary carbocation. 2 other carbon groups on that carbon. Could we move a hydrogen from here next door? Well, we could, but then that leaves the positive charge on that carbon, and that carbon is still secondary. So a secondary carbocation turning into another secondary carbocation. Again, I've said it can happen in cases, but for our purposes, no, so that's not going to happen. And what about this third case? Well, notice that here we have a secondary carbocation, again 2 other carbons attached to us, so that's secondary, and on the carbon next door we have 3 ethyl groups. So could we move one of those ethyl groups next door, just shift this pair of electrons over to here, there it is, and in so doing then this carbon loses an electron and it's the one that becomes positive. So what kind of carbocation is that? 1, 2, 3 other carbons attached, that's tertiary. So we've gone from a secondary to a tertiary. That could happen, and you would have to predict that would happen. So now, let's look at some stick figures. These are a little more complicated. Well, I shouldn't say complicated, but a little bit more difficult to judge because you can't see all the hydrogens. You have to realize that they're there. In some cases, you might actually literally draw in hydrogens in order to figure out what's going to be positive and what's not. So these are 3 perfectly fine carbocations. And I want you to stop the video, write them down, and then see if there's a rearranged carbocation that could be better. This is a secondary carbocation. That's a CH and 2 other carbons attached to it, so it's secondary. If we move one of these methyl groups over next door, that would become this. So one of those would move to here. That's this one it's moved. That would leave then this carbon positive. That's this carbon. That then would be a tertiary carbocation, so that could happen. And that's a pretty straightforward rearrangement. And one that may not be quite so obvious, though, is that this whole group right here could move. In other words, this carbon right here actually has 2 methyl groups and an ethyl group. One of the methyls could move. Of course, the other methyl could move as well, but that would give you the same thing. But could the ethyl group move? Could this ethyl group move over to here? If so, that would leave this carbon positive, and that would then, on this carbon, you'd end up with the extra ethyl group. So there it is. What kind of carbocation is that? That's tertiary, just as this one is tertiary. So this one is kind of a special case where there's actually 2 different rearrangements that can occur, and chances are pretty good that if you did get this carbocation, both of these rearrangements would occur. Okay, so what about the second case? Well, this is a secondary carbocation. Could we move anything from one of these carbons next door to make it into a tertiary carbocation? If you state it in that way, it becomes obvious that there is a hydrogen right there that we could move over to that carbon right there. So that carbon now has 2 hydrogens instead of only 1 that it had in this case. But as when we move that hydrogen over, that leaves this carbon positive, and that, of course, is a tertiary carbocation. So that would occur. Let's take a look at this one, slightly different case, although similar. Again, we have a secondary carbocation. Could we move something over from either of these 2 carbons? Well, clearly we can move a methyl group from here over to here. That leaves now the methyl group attached to that carbon. This already had a hydrogen, still has a hydrogen. So the only difference here is now this has a new methyl group. But in so doing, this carbon loses an electron when the methyl group moved over, and so this carbon ends up being positive. It only has 1 methyl group now instead of 2. Notice it had no hydrogens to begin with. It still has no hydrogens because it's positive. That's the end of this lecture. Thank you very much.